Hello, thank you for attending our talk. Our paper discussed here is entitled Reducing Textural Bias Improves Robustness of Deep Segmentation Models. MRI scans are used widely in medical imaging, and CNNs can be trained to carry out classification and segmentation tasks on them. However, because the images contain visual noises and low-frequency textual patterns that are inherent to acquisition protocols or hardware, the models that are trained on one domain often don't perform well in images from another domain. Then, wouldn't it be nice to just train the model once and use it on images of multiple different domains? To investigate this, an idea from the paper, ImageNet Trained Models are Biased Towards Texture, was used as an inspiration for our research. This is part of an experiment that was carried out by the works of A.I.L. What can you see in these images? Well, most of us would be able to guess that both of them are pictures of a cat. Humans tend to distinguish objects by looking at the global shape patterns of an image. Now, the picture on the left was actually created by combining two different pictures together, which are the texture of an elephant as shown on the left and the shape of a cat as shown in the middle. These two images are combined to give the rightmost image, which has the shape of a cat and the texture of an elephant. The researchers found out that their model classified it as an elephant rather than a cat, showing that the model made the decision based more on the texture than the shape, unlike what the humans would do. The researchers then investigated the way humans carry out image classification tasks, which involved human participants. They found out that humans carry out classification based on the object shape more than the texture. Finally, they investigated the textural bias property of CNNs and trained a model which is robust to the texture. In our paper that we present here, we carried out experiments to investigate the textural bias property of CNNs in medical imaging setting. Our contribution is an extensive empirical study consisting of 176 experiments, which demonstrated that training a deep segmentation model on data corrupted with certain combinations of texture and noise can in fact improve the model of robustness on new, previously unseen noise types and levels. We believe that this is due to the models being incentivized to learn anatomical and tissue-specific features during training, as opposed to low-frequency textural patterns that may be brittle and domain-specific. In terms of data, we use a publicly available dataset from the Developing Human Connectome project, which are 3D T2-weighted grayscale brain scans of babies. A total of 70 scans were used in this project, where they were split into 50 training, 10 validation, and 10 test sets. This is a fairly complex tissue segmentation task because visual characteristics of the scans can greatly vary throughout brain development. So for example, as the brain matures, the occurrence of dark intensities present in the white matter regions gradually increases. Since the motivation of the experiments was to find out whether training models under a certain textural noise setting could potentially help with the domain shift, some of the noisy data sets created above were intentionally not used during model training. 3 different types of texture filters we used to change the texture of the brain's images, which will represent the domain shift problem in the medical imaging domain. Blur is one MRI artifact which can be introduced into the scan after an acquisition stage, such as during post-processing or in the manifestation of pathological conditions. To represent this, we apply the Gaussian filter function from Scikit image library, where it takes in sigma, which determines how blurry the output image should be. The second transformation is the medium filtering, which is another type of blurring used in this research. This replaces the pixels in the images with a median value of their n-close neighbors. An implementation from Scikit library was used to generate the images. We also explored impulse noise corruptions, such as those introduced by noisy communication channels, faulty memory locations, or damage in channel decoders. The impulse noise generating filter we used in the study is the salt and pepper filter, which introduces white and black speckles in the images. Higher value of the user input probability introduces more speckles in the images. All images from the dataset were normalized before applying any filtering on them. 5 Gaussian filter images with sigmas 1, 2, 3, 4, and 5. 7 salt and pepper filtered images, probabilities 0.01, 3, 5, 7, 0.1, 0.15, and 0.2. And 3 medium filtered images with n, 2, 5, and 8 were created for the experiment. The segmentation network architecture used in this experiment is based on DeepMedic, an open source 3D framework with multiple convolution pathways, which was originally built for brain lesion segmentation tasks. A dual pathway scheme, which processes the input at multiple scales, as can be seen by the 2 pathways in the image, is used so that the network can capture both the local and larger contextual information. The model can be configured to have more than one subsample pathway, which was the case for the model used in this project. Optional residual connections and various other parameters can be also configured to train and test the model. This table shows 11 models we trained for this experiment. The left column shows the name given for the model, and the right column shows which datasets were used to train the model. So for example, SMP010510 was trained using 3 salt and pepper filtered image sets, each with probability 0.01, 0.05, and 0.1. Each of the 11 models were then evaluated on 16 held out test sets. The total number of experiments carried out was therefore 176. Different variations of unseen images, as shown on the slide, were purely reserved for testing purposes. This was to simulate the domain shift in the medical imaging setting and to find out whether the models we trained gained robustness in the MRIs with unseen noise. In terms of evaluation metrics, dissimilarity coefficient was used, which is a metric that measures how close the predicted image is to the ground truth image. For succinctness, we present in detail 3 of the 11 models, showing the most insightful results in the tables discussed next. This table shows the performance of the noise-free model, MT2 original, when tested on 16 held-out test sets. From the table, we can see that the model generalizes well on the datasets that were lightly filtered. However, for all the other datasets, the model did not show a good result. The row highlighted in bold indicates a dataset in which the model segmented all classes with DSCs higher than 0.9, meaning that the model gave an excellent performance on all 10 classes in this particular setting. The results in this table therefore show that the baseline model trained using a conventional approach does not immediately generalize to unseen noise categories and levels, highlighting the domain, a problem with domain shift often experienced a wide range of realistic scenarios. The model SMP10, which was trained on a high level of salt and pepper noise, demonstrated high levels of robustness on all 10 classes for noise-free data, T2 original, data injected with lower levels of salt and pepper noise, SMP01, as well as higher levels of salt and pepper noise, SMP15. Although not all classes have reached 0.9 in all test sets, the model shows really good results in median 2 and gas 1 images where the transformation is light. And these are some predicted segmentation labels from the model as well as the ground truth image. We can see that the model shows a good performance on a highly corrupted SMP image, but performs considerably poorly on data corrupted by Gaussian filtering. Finally, the model trained on several levels of Gaussian and salt and pepper noises exhibited the best overall robustness across all levels and types of noise tested, as well as on the 10 classes studied. The model showed good results for all datasets, even for the cases of Gauss 5 and median 8, which are the datasets the model performed the worst. DSCs didn't fall below 70%. These are the predicted segmentations of the models on the heaviest transformed images of the 3 filters used in this investigation. We can already see that all of them achieved a decent segmentation, although median 8 and Gauss 5 misses some details. However, compared to results obtained in Gauss 2 images generated by model SMP10 previously discussed, results in Gauss 5 here look a lot better. From the experiments, we could see that the models trained on Gaussian filtered images only generalized to Gaussian filtered datasets generated using the similar sigma values. Median trained models generated to lightly filtered median and Gaussian images, but not to SMP filtered images. Salt and pepper trained models, however, showed good performance on other SMP filtered images, as well as on the original dataset and on lightly filtered median and Gaussian datasets. Finally, the model trained using variations of Gaussian and SMP filtered images was good at segmenting almost all datasets used in this project, although the performance was not sufficient enough on some heavily transformed images. From the results, we can deduce that the models trained on images corrupted with impulse noise generalize well on similarly generated images, as well as median smooth images. Hence, training on such images could help the model move away from the textural bias and take useful anatomical shape information more into account when carrying out segmentation tasks. The models trained on smooth images only seem to generalize on images that were smooth to a similar degree, and not at all on images with impulse noise corruptions. These findings suggest the possibility for easing the domain shift problem in medical imaging models by introducing SMP noise and smoothing in the images instead of using the images directly on training the segmentation model. Thank you for listening.